Okay, welcome back everybody. We're moving on to section 1.2. This is called Domains and Boundaries in D dimensions. Basically what we want to think during this section is that if we have a function phi which solves a PDE, then phi has a domain. And importantly, this is going to be, the domain is going to be some subset of D-dimensional real space, which is open. Actually, there are two things, open and connected. Why open? It turns out you can only find derivatives in open spaces, and then connected because if it were disconnected, you could just reimagine two independent PDEs, each evolving on a different domain. You could separate disconnected parts into multiple parts. So we're looking for a subset of RD which is open and connected, and we're going to call these the domains. And often we'll talk about them as domains of PDEs, even though they're really the domains of the solutions to PDEs. Okay, well, if we jump back to ODEs, we often make this distinction between initial conditions and boundary conditions, right? So initial conditions are where the values of the solution are defined at one point. This is in some sense in ODEs. I'll have something like y of t solves an IVP if we have something like this. Y prime is some function of t and y, and we have y at the initial point has a value, y0. And it's the second term, y at the initial point, that tells us that we have an initial value problem. But in fact, you can have initial value problems with higher derivatives. Something like that would be a second order initial value problem, and you just have to add an extra term at the initial value, call it y sub 1, and it's equal to the value of the derivative at the initial point. Okay, and this is because, how does this relate to domains? In some sense, this t0 is the boundary of our domain. Right, so y, which is the solution to an ODE, its domain, its input, its collection of inputs are going to be time, and they're going to be allowable from t0, the initial time, to infinity, so that we're looking at the boundary. The boundary of t0 to infinity is going to be t0. And alternatively, in ODEs, we can have boundary value problems, and this is just where the boundary is 2 points instead of 1 point. So let's look at an example of that. Maybe y double prime is f of y prime in t, but now we have defined the value of the solution at 2 different points in space. Right, and these points in space are now called our boundary conditions or boundary points. That's because if we have a solution, y of x, what does the domain look like? In fact, the domain is really x is in this interval. And what is the boundary of the domain? The boundary of the domain are the 2 points, x0 and x1. So the difference in ODEs, it's really a choice between 1 or 2 points. If you have 1 point, that's the boundary of your domain, that's the initial condition situation. If you have 2 points that are the boundary, that's the boundary condition situation. In PDEs, things get a lot trickier because if I have some function, let's say phi of x, y, and z, and I allow x to be in some interval, I allow y to be in another interval, and I allow z to be in yet another interval. That's just a rectangular prism, but the boundary of a rectangular prism is certainly non-trivial, right? The boundary of this sort of object is certainly a non-trivial boundary, right? It's going to be anything on the front, anything on top, anything on the side, right? The boundary is a full plane, or it's a subset of a plane. It's not just 2 points. And so boundaries and domains get a little bit trickier when we give ourselves the ability to work in multiple dimensions in the domain of our solutions. So that's what we're going to be focusing on, is we're going to be focusing on the domains of our solutions as well as their boundaries. We're going to allow ourselves an arbitrary number of dimensions. And it's going to be a little bit tricky because we're in PDEs land instead of ODEs land. So we're going to focus on, I'm just going to give a quick, not formal definition of each of them. but the domains is going to be the set of independent variables a PDE needs to be solved within. A boundary is going to be the edges of the domain upon which a PDE is paired with boundary values or conditions. And normal vectors are actually going to be really important because these are going to describe the directions in which a point which points away from a boundary. And this gives the ability one to calculate directional derivatives in those directions. So let's go back really quick to the idea of solving a PDE over a rectangular prism. It may be quite relevant to calculate the directional derivative of our solution in all of these directions that point out of the rectangular prism. This is important because the phi xyz, if we're taking multiple derivatives, to gain uniqueness, we actually need to know these values. To gain uniqueness of solutions, we're going to need to know the values of the directional derivative of phi pointing out of the boundary. Okay, so that's what we're looking at. Let's actually head into some definitions here. So the definition of a domain is going to be any open connected subset, and I'm going to call it omega. So we're going to get used to this Greek capital omega to mean an open connected subset, really a space that we're going to be solving differential equations over. And it's going to be a subset of RD. I'll sometimes allow ourselves to be a subset of the complex numbers, but let's just basically think about RD most of the time. And to be connected, it means that any 2 points in omega have a continuous path completely contained within omega between them, right? So we can think maybe very classically about two-dimensional connected sets. This is a nice example of a connected set in 2D, because no matter what 2 points I take, let's grab a point here and a point here, I can find at least one continuous path through omega which connects those points. An example of a disconnected set would be something like this, where if I grab 2 points and I try to connect them, all of a sudden there's this gap in the middle where I'm not in omega. So that would be an example of a disconnected set. So connected just means I can connect any 2 points with a continuous path. Disconnected would be the opposite of that. Now open corresponds to, for each point, there is at least one ball completely contained within omega, also containing the point. So open, for example, I shouldn't draw this with a fixed line on the outside. I should actually draw it with a dotted line on the outside, because what it means to be open is that I can't include any of those points on the boundary. I have to grab a point inside omega, because if I'm open, there's at least one ball contained within omega containing the point. So notice with this point, I can find a ball that encircles the point that also is sitting inside of omega. You can imagine a not open set would be an example like this, where I've actually closed to the boundary, because if I choose a point on the boundary, let's choose this point here on the boundary, no matter how small I try to make a ball around that point, I will always run into something outside omega, right? So the ball around that point will always run into something outside omega. So to be open, we just can't include that boundary. Looking at some examples, jumping back to ODEs, the open intervals are in fact domains. These are the intervals we would solve ODEs on all the time. You would see boundary value problems on an open interval with finite endpoints. Initial value problems would be an open interval with like 0 as an endpoint. And in fact, there are some ODEs that you can define on the entire real line. They're not really either initial value or boundary value problems. You kind of think about boundaries at infinity if you want to for the full real line. These are all domains. They're trivially connected. Let's verify that. So let's grab the open line segment between x0 and x1. It's certainly connected because everything inside there can be connected to itself. And since I'm not including the endpoints, as long as I grab a small enough ball around any other point, I still end up in there. And that's because I'm not including the endpoints. Certainly the half line satisfies this as well. If I start at 0 and go out to infinity, certainly that's going to be true. I can connect any 2 points if I choose them. There's my connection, and if I grab a point, I can find a ball around it. And then the real line with infinity on both sides, certainly I can connect any 2 points, and I can find a ball around any point. Now the ball has to be reduced to 1 dimension in that case, so it's really an interval itself, but you get the idea with balls at least staying inside of the domains. So we can jump into higher dimensions. Let's look at some nice examples of higher dimensional objects. This is called the open hypercube. So if I take the interval 0 to 1 and I take powers of it in the sense of I start with my open interval 0 to 1, the second power of this would jump into the second dimension, and I end up with a square. And it's going to be filled in. So this would be like 0, 1 squared. I could do 0, 1 cubed. Let's choose a new color. 0, 1 cubed, I have an open interval. I then make the open square. I then make the open cube. And then imagine this was filled in, except for the edges. That's my open cube. I could have the open tesseract. I hope I could do a good job drawing this. Nobody likes drawing four-dimensional objects, but I'm going to do my best to draw the tesseract. All right, there's my tesseract. If that were open, right, if I'm not including the edges, then I have my four-dimensional open cube, and we can continue to as many dimensions as we want. All right, so that's some good examples. If we talk about the domain of a differential equation, the domain is just going to be any connected open subset upon which all functions and the solution set are well defined, right? So like I was saying at the beginning, if I have a solution to a differential equation, what is the domain of the function which solves it? And that's going to be the domain of the differential equation. So let's look at an example here. I've paired the heat equation, which we encountered in our 2 videos ago, I guess. I've paired the heat equation now with a domain rather than just saying inside the metal and outside the metal. I've written some mathematics which can actually describe the shape of the metal for me. And that's this entire piece here, which is a little frustrating to have to put up with all the notation, but you know, you can only do so well sometimes with notation. What is this notation actually saying? Well, it's saying that the temporal variable is allowed to exist in the forwards direction starting at 0. So this would be my time axis. And then I'm allowing x, now recall that's going to be the vector of all spatial terms, so it might be higher dimensional than just 1 because it's in boldface. I'm allowing x to actually be the set of x, y's, and z's, where this expression x minus 1 squared plus y squared plus z squared is less than 4. And then this symbol here is called the union. It just means I'm adding the set here to the set here, and I'm going to consider both sets together, where now I have x plus 1 plus y squared plus z squared is less than 4. So let's actually think about what that set might look like, this one. And to do that, we're going to jump over to the blackboard. Okay, so here we are at the blackboard, and if you recall, what did my domain look like? Well, I said it was that t was in 0 to infinity, and we had this set of x minus 1 squared plus y squared plus z squared is less than 4, union x plus 1 squared plus y squared plus z squared is less than 4. And really, we don't have to worry too much about the t term because we know what that looks like, but let's try to visualize maybe what this boundary looks like. So what's going on here? We've got x squared. If we just pretend like that were an equal sign and not a less than sign, we've got something like x squared plus y squared plus z squared equals 4, except I haven't shifted x yet, and that's okay. We should recognize this as the equation for a sphere of radius 2. So if I draw my 3-dimensional axes, we're looking at the sphere of radius 2, which is something like this, as long as that point is 2. So there's my sphere of radius 2. If I decided to shift x to x minus 1, that's actually moving the sphere to the right by 1. Okay, so we're going to clear everything and think about this sphere that's now been shifted to the right by 1 unit. It's going to look something like, there's my circle part, there's the front half, there's the back half, coming up front here. So my sphere looks something like this. That's going to be the original term here. Now the second case has just been shifted to the left instead of shifted to the right. So I'll use black still, and then we've got a sphere that's been shifted to the left. You can imagine what is the less than sign. Less than 4 means I'm inside the sphere. We're actually inside both spheres. And this union means I'm just inside both spheres, right? So we're gonna look at the inside of both spheres. Let's just highlight it. They're gonna intersect in the middle, and we've got this sort of a three-dimensional shape. It's kind of like a dumbbell, but it's a squished dumbbell. It's the intersection, or it's not the intersection, it's the inside of both of those spheres. That's the domain in our example. Okay, so that's a visual idea of the domain, and then we'll talk about the boundaries, because the boundary is actually what's really important when we're talking about these outward normal derivatives. So the boundary of any connected open set is going to be the unique set, and here we have a special new notation, partial omega. Okay, so it's a new notation. It looks like a partial derivative. It's not actually a partial derivative, but it looks like it. It's called partial omega, or the boundary of omega, for which every ball around every point in the boundary has a non-empty intersection with both omega, the domain I care about, as well as what's left over. So let's think about this term here. That's another collection of math symbols. This is everything but omega. So we have an intersection with both omega and everything but. Every ball that surrounds one of the points in the boundary needs to have this property. So let's look at an example. If I jump back to, let's do an open connected set. So I give myself the dotted boundary because I'm not including the boundary. How do I construct the boundary? Well, all I do is I find a point where every ball around that point will intersect omega on one side, and it'll intersect everything else, which I denote like this, on the other side. So everything on the boundary, the balls satisfy these properties, and that's how I actually define the boundary. So we can define the boundary by every point which satisfies that property, and that gives you exactly the intuitive boundary that you would think about. It's this collection of points. So that's the boundary. Let's look at some examples of the boundary in one dimension maybe. If I have my open interval x0 to x1, the boundary is just going to be those points. And when I use this notation with the curly brackets, that just means I'm building a set. So I'm building a set in this case of 2 points. The points are x0 and x1. And so that's going to be the boundary of an open interval, right? So here's my interval, x0, x1. Its boundaries are actually these points. If I have the infinite interval, then in fact this doesn't have a boundary, and this is another fancy notation we have called the empty set. Okay, so I'm just saying this infinite interval doesn't have a boundary. And you can imagine if I put an infinite interval on one side and not the other side, the only point that I could possibly pick up on the boundary is the non-infinite side. So a nice example again with this interval starting at 0, the only boundary point is right there. So that's how boundaries work in one dimension, but we can jump to higher dimensions with the hypercube. And let's just think about it before I go down too much. Let's think about it with just the square, right? This 0, 1 squared is in fact, like I said before, you go open, 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 and really those boundaries should be open. So I'll erase those and include dotted lines instead. But I'm filled in on the inside, I just don't have the boundary itself. So that's my open square in 2 dimensions. If I look at its boundary, the boundary of the open square is the square itself, but now it's empty, right? So the square itself gets filled in, but the inside is now empty. That's going to be the boundary. And how could I express this collection of points? Mathematically, it doesn't have the world's best expression. This is the point 0 and the point 1, and they're going to be crossed with the entire interval 0, 1. So what does that look like on here? Here's the point 0, here's the point 1, and they get crossed with the entire unit interval 0, 1, right? So this is the full interval 0, 1, 0, 1. So that's producing those 2 edges for me. The second case here, the interval 0, 1 crosses the collection of points 0 and 1, and that's going to be these other points. So the entire unit interval 0, 1 gets attached to 0 in this side, and it gets attached to 1 in this side. So that's how we could mathematically express it if we wanted to. You're not going to be asked to mathematically express these too often, and we'll see that there are actually easier ways of doing that in a bit. But that's how we can mathematically express the boundary of the unit square. And if we jump down to the hypercube, we get some really nasty notation. So the hypercube has a really easy definition. It's just 0, 1 open to the d power. But if we try to express the boundary, we start having to use some really intense notation. And I don't want you to have to spend too much time thinking about this notation. It's really ugly. It's not going to be relevant for a lot of the stuff that we discuss in this course. But I want to let you know that it's possible to reproduce the boundaries using some formal notation if we wanted to. Now we can talk about the closure of a set, and this is pretty important. It's just the collection that contains the set itself, and then this is that union symbol with its boundary. So I'm just attaching the set itself to its boundary, and I'm going to call that the closure. I'm going to give it the notation of an over bar, or I'm going to put a bar over my omega. So now we can think a little bit more easily about my unit square. And if it's filled in on the inside, but the boundary doesn't exist right now, if I wanted to close it, I can close it by attaching it, and this is it, to its boundary, which is that, and then all of a sudden, you would probably agree with me that that's now a closed object. So that's what it means to close a boundary, or close a domain. And we can look at the closure of open intervals. It's just what you would expect. The closure of open intervals are the closed intervals. If I have the open interval between 0 and 1, I've attached it to its boundary, and I recover the closed interval. Minus infinity to infinity, since the boundary was non-existent, it just stays the same, and that is in fact a closed interval. And if I have a half line, I'm going to close only the finite side of the half line because the infinite side was already closed. And then we can talk about the hypercube as well, and it turns out it's a lot easier to write the closure of the hypercube than it is to write its boundary. The closure is just going to be the dth power of the closed unit interval. Okay, so then let's talk about level sets, super level sets, and sublevel sets. The really important part of this section is actually the interaction between these objects, level sets, and boundaries, because we can actually realize boundaries as level sets and level sets as boundaries so that we can avoid this really bad notation for like the boundary of the hypercube. We don't like using that notation. We can actually use an easier notation using functions and level sets to describe boundaries instead. So let's talk about level sets first. And the notation here is interesting. Okay, so it looks like f inverse. So the notation is the same as for an inverse function. Notation agrees with an inverse function, but the astute among you will notice that rather than putting a variable into the inverse function, I've actually placed a set. This is a set inside of the inverse function. And what this object is called is the preimage. So the object is called a preimage, but more or less when we take the preimage of a set with only one entry, so that case is the set that contains y, the preimage of a set that contains only one entry is a level set. Okay, so we're going to call the level set of level y, it is the preimage of the set that only contains y, but how is this set actually defined? It's defined as the following. Now you'll recall from previous videos that I'm calling this set builder notation, where on the left-hand side, we're looking at a collection of objects. These objects are x's in some d-dimensional space, and on the right-hand side is a property that those objects have to satisfy. So I've got my collection of objects, collection of x's, these are vector x's, which satisfy, in this case, they satisfy the property that f of that vector equals the value y. So my function here, the function I care about, when I compute its output on the input of x, I need to get the value y out of it. This is called a level set. So let's describe maybe why we call it a level set. Jumping back to calculus 3, let's consider a case of maybe f of xy is 1 minus x squared minus y squared. Now this looks like the paraboloid. It's a downward facing paraboloid. If I draw it on an x, y, z axis, I have a downward facing paraboloid. And if we look at maybe the level set, let's go with the level set of level, let's do level 0, then what we're going to do to find this is we compute a slice. We compute the slice of my surface, which is this paraboloid, through the z value 0, or through the f of xy value 0. And there it is. So this is where f equals 0 on the surface. And we've sliced it, and we're going to look at the set of xy's. Level set of level 0 is set of xy, which give 0. Okay, so this set of x's and y's, it looks like a circle of radius 1, is going to be the level set of level 0 in this situation. So that's why we call it a level set. It's a set of inputs on which a function is level, right? This function is level along those inputs. It doesn't increase or decrease. And we use this notation to describe it. But we can think about those as boundaries, right? Because jumping back to earlier, if I have some boundary of a set that looks like that, you could ideally construct a function for which it's level along that specific curve. So the boundary and the level set are the same thing. We actually already have an example of this. If I jump back to the whiteboard, here I am back at the whiteboard. I wasn't calling it the level sets at the time, but in reality, what was going on here is that the boundaries are level sets. So the boundary here, right, is x minus 1 squared plus y squared plus z squared equals 4. If I think about that as a set, that is a level set. It's a level set of the function. There's a function of x, y, and z, and that function is equal to 4. So this is the level set corresponding to 4. And in fact, that does work out to be the boundary here, the boundary being the surface of the spheres themselves, right? So if I looked at the level set that included both of these, actually I need a new function for the second case, but the level set that includes both of them, or you could construct a piecewise function maybe, that includes the level set of both of them, you recover the boundary of this domain. So we've seen them before, they were just a little bit hidden. Okay, so speaking of that then, we can talk about superlevel sets and sublevel sets as being above or below the level sets that we are thinking about. So let's jump back to our paraboloid 1 minus x squared minus y squared, which we had drawn as the following. So there's my paraboloid, and we can think about a superlevel set. So let's jump back to the same case where we had 0. This is my level set of 0. Super level set, everything above 0. So I'm just going to be looking at the paraboloid where it's above 0. And then to actually talk about the set, I think this is important. We should really emphasize this, that the set is only the values in the domain. Okay, so it's the values in the domain of the function. So that's actually everything inside of the circle, because I'm projecting down to xy plane. So even though, all of the terms that are above the circle I originally considered are up above, I project all of those terms down to the xy plane and actually cover the filled in circle. So that's a super level set. A sub-level set is exactly what you would expect. It's the opposite of all of that. So in the paraboloid, it's everything below the set 0, and then you project that onto the xy plane, you would get everything that's not the circle in the middle. You'd get everything outside of the circle. So sub-level sets, we're looking at values of a function below a point, and then we're looking at the inputs. So we project onto the domain. Super level sets, value of a function above a level, and then we look at the inputs. And so these are really important because we can just construct domains, right? We can construct domains as super or sub-level sets. We can construct boundaries as level sets. And this proposition just kind of reinforces that you can actually do this. I won't get into the proposition too much. What you should be taking away from this is that a lot of times our domains omega, we're going to write them as f inverse, or the preimage of the half line 0 to infinity. We'll write boundaries as the preimage of 0 of some function, and this function is going to be an important function. So really this is what I'm trending towards, is just having you realize that domains are super level sets for functions, and their boundaries are exactly the preimage at 0. So it's the preimage at a boundary. So it's really interesting, right? Because what are we doing here? That is an open connected set, and we are mapping it to another open connected set. And the same thing's happening here. This is the boundary of the open connected set there, and we're mapping it to a boundary. So it's really nice that we can think about really starting with the basic open set of 0 to infinity and the basic boundary of 0. And underneath this function f, we can basically recover anything we want. And the proof goes through the way of constructing one such function, but then I have a remark where I say the function in this proof is actually really not important. Most of the time, we are going to be defining a domain as a super level set, right? A super level set of a continuous function. And we can jump back to the whiteboard and see that. All right, because here I am back at the whiteboard, and you'll notice that actually we ended up defining the domain here as super, I guess in this case, sub-level sets, because I've used the less than sign. But we define the domain really as sub-level sets of this function here. Not that, but that function. So we defined the domain as the sub-level sets of that function, and then the boundary we recovered by finding the boundary of the sub-level set, which was the outside of these spheres. So a lot of times we're just going to start out by defining a domain using a function, and then we're going to be able to compute its boundary by looking at the preimage of 0 of that function, or something similar. Okay, so why is this actually important? This is important for something called the outward unit normal vector. And of course, I already teased this at the beginning of the lecture. But what we're trying to think about, maybe if I jump back to the whiteboard, what we're thinking about here at the whiteboard is constructing the vector where on the surface here it points out, it points away from the surface in the normal direction, right? Maybe over here it points out that way a little bit, there it points over there, and so on. So we have these vectors that always need to point normal to the surface, and we would like to compute those. And this is not always the easiest thing to do unless you decide to write your domain or boundary as a level set or super level set of a function. So let's look at some examples of these. We can start just with the unit square. So I've gotten gray the omega, right? So I've made omega gray and I've made the boundary of omega red. So I've got a unit square here. And we're going to ask a question about the outward unit normals. It's actually really easy to figure out what they should be. These are the vectors which point outward, which I have as 1, 0 if I point to the right, 0, 1 if I point up, negative 1, 0 if I point to the left, and 0, negative 1 if I point down. So it's really not hard to do in some very simple cases, and we can do the same thing for the unit disk. Here I've defined the unit disk as the set of points for which x squared plus y squared is less than 1. Here you can start to see this is really pushing on sub, right? This is sub level set territory, because that is, in some sense, the definition of a sub-level set. It's a function on the left, and it's less than a value. And so we're sitting at sub-level set territory, but you can also just interpret this directly as a domain, which is the unit disk. And so omega looks like the following, right? It's the unit disk, and its boundary is, of course, the boundary of the unit disk. And we can purport pretty easy unit normal vectors for this too. You'll notice that all of these that I've drawn here, they all take the form cosine theta, sine theta. So this one would be cosine 45 degrees, sine 45 degrees, if you like working in degrees instead of radians, 1 over root 2, 1 over root 2. Right, so that's the vector described there. Here, this is the vector 1, 0, and so on. So you can purport these unit normal vectors fairly easily in fairly simple problems, but it does start to become tedious, because let's jump back to the whiteboard. Right, it's very tedious on this whiteboard to try to figure out what all of those outward unit normal vectors would be. Certainly something like this is fairly easy to purport, but something over here is going to be a little bit trickier. And so we're basically going to work towards what is the natural way of finding these outward unit normal vectors. And the easiest way to find them is by considering the super and sub-level sets for the definition of omega itself, which is why I had the earlier proposition. So supposing that we have a domain, a boundary, and some function, which allows us to write the domain as a super level set, and it allows us to write the boundary as the level set of level 0, then I can compute the outward unit normal vector as the negative ratio of the gradient of f over its magnitude. And dividing by the magnitude just normalizes this vector to make sure that it's unit length. That's why I use the word unit there. So that part isn't too terribly important. The negative is important because I'm using this word outward. If I wanted it to point inwards, I would have a positive sign there. And the gradient is really the special thing we're going to be computing here. So let's jump back to the whiteboard. And I'm going to show you really quick that I could compute this one, this outward unit normal vector, by looking at my function, right? My function is f of x, y, z. And this is the function on the right-hand side, right? That's the right-hand sphere, so I'm going to be looking at the function right here. This is x minus 1 squared plus y squared plus z squared. I'm going to compute negative gradient f divided by absolute value of gradient f, or magnitude of the gradient of f. This is going to be my outward unit normal. And it's not too hard to do. Let's recall the gradient of f. It's the partial derivative in x, the partial derivative in y, the partial derivative in z. We can do that fairly easily looking at our function. Partial derivative in x is 2x minus 1. Partial derivative in y is 2y. Partial derivative in z is 2z. If I divide that by its magnitude, what do I get? I get that the normal, and I add a negative sign, is going to be 1 divided by the square root of each of the entries squared. That's the magnitude, so I'll get 4x minus 1 squared plus 4y squared plus 4z squared. That's me dividing by the magnitude, and then I recover the entries themselves. And that's going to be my outward unit normal. So supposing maybe that's the point, I can't really tell what that point would be. It's probably like, let's say it's 1 for x, 1 for y, and whatever z would have to be then. Z would have to be, I guess, the square root of 3. We could factor this out and find out what it actually is going to be equal to. So that's how we produce the normal at any given point. It's a lot easier than just purporting it and crossing your fingers that you did a good job. And we'll jump back to the text. And so now let's see this proposition in action for our two previous examples. So if we want the unit square, the outward normal for the unit square, we can actually construct a function. Here's my function. It's a little bit ugly, but we can construct it, a function for which the unit square is a level set or a super level set. So there's a function that I've constructed. It's piecewise. And if I plot this function and look at the super level set and level set, we get the following, right? So in red, there's my, or I guess I've inverted the colors, but in the boundary, that's my level set is the boundary of omega. And the super level set is that pyramid shape because that's everything above the boundary. And so you can see in gray, I've filled in everything inside the square, and then on the outside of the square, I have the boundary. And if I go ahead and compute the gradient of this f and divide by its magnitude and add a negative sign, guess what I get? I get exactly the 4 outward normal vectors we would have expected. And so we exactly recover the outward normals we would expect. We can do the same thing for the disk. And in fact, we've seen this as the paraboloid. Let me rearrange this really quick. We can rearrange this to 1 minus x squared minus y squared is greater than 0, right? And when I do that, I define that as my function, 1 minus x squared plus y squared. And there is my super level set, the inside of the circle, as well as its boundary around the outside. And I can go ahead and compute this outward unit normal. And guess what I get? I get x over y, which, if we parameterize the outside of the circle, is cosine theta over sine theta. So I do get exactly what I was looking for in previous cases. And I do want to stress that the main reason we care about this is because we can just start by defining domains as super or sub-level sets. It's just part of the definition. You should almost always see the super or sub-level set on the right-hand side of the definition of a domain, because this is the easiest way for us to do it. And then we can almost immediately construct this function that we're going to take the gradient of to compute outward unit normals. So this is a 4-dimensional function. It's not too easy to try to purport outward unit normals, but all we have to do is actually compute a gradient. We go through the process of computing a gradient and look at what we get. I've simplified it a little bit because of some properties that we know it must satisfy, but you immediately recover that outward unit normal as this 4-dimensional vector, which depends on x, y, z, and time. Anyway, that's all I've got today. We'll be moving on to ODEs in the next video. I'll see you then. Bye.